All right, welcome to today's lesson. Today's lesson is on dilations, and I'm just going to run through a few terminology things that I need you to think about while we're doing this, and then we'll get into it. So the first one is that you need to think about dilations being a stretch, as opposed to translations, which were a move. So dilations are a stretch. The second thing you need to think about is a couple of terms. So I'm going to refer to dilations as being from the x-axis. And what this means is you have a small person who's standing on the x-axis and they are watching whatever function it is move closer to or further away from them as they stand on the x-axis. So from the x-axis can be thought of as a vertical dilation. The next term I'll use is from the y-axis, and just like you might expect, imagine there is a small person standing on the y-axis and they are watching the whatever function it is move closer to or further away from them. So from the y-axis can be thought of as a horizontal dilation or stretch. All right, now have a look over here on the Desmos screen and you'll see that I've got a square root function, f of x equals root x. You'll notice that I've used function notation. That's because in these folders that are hidden, I've got some special calculations happening which refer to the functions. So you'll notice here that there is a equals 2, just here. In both of these folders, that a value is in place in the function as a dilation, and I'll show you that later on, but not right now. All right, so the next thing we need to remember or have a look at is we're going to have a look at dilation from the x-axis. So you can see here that this blue line, this function has been dilated from the x-axis. You can see that it's moved further away from the x-axis, and you can also see that the x value hasn't changed in the blue one, so 9 is still 9. However, the y value has doubled. And if you look at this a value of 2, I can tell you that's the dilation factor. You should be able to tell me that obviously the y value has been multiplied by 2. So what you should also be able to tell me is where that would sit in the function for that to happen. So let's have a bit of an explore as where that would take place. So we know the original point was 9, 3. All right. We know this is xy. We know the image point is 9, 6. And that's written like so. All right, I'll just move these slightly. So we also know that the a value is 2. So let's have a look at how we can make that happen. So we could say that the image of x equals the original, and we can say that the image of y equals 3 times a. And if you wanted to write that in terms of x, you would say that it was, y, the original y has been multiplied by whatever a is. Now, if you remember how we did this last time, you remember that you have to get this in y equals, so you'd need to divide by a, so the image of a, y over a equals that. And then you would substitute this and this into the rule for the new function, so you would have y equals, oops, I won't use f of x, I'll use root x. That's the original. So now we have y image over a equals square root of the image. And then you're going to have, to get the y by itself, you're going to multiply the a to the other side, so it's going to be image a root x. So there you have a sitting out the front is dilation from the x-axis. All right. So one way of thinking about it is that it looks like this. It sits out the front of whatever the function is. So whatever happens to x happens, and then it gets dilated away from the x-axis. So looking back to the Desmos screen, let's see if that holds true. If I move this red dot along, we'll find another nice square number, 25. You can see here that the original one, the red one, 25, 5, has been pushed out by a factor of 2 again to 25, 10. So the same x value, but the y value has been pushed out. And 36, 6 has been pushed out to 36, 12. So it's happened again. All right, and as I change this a value, you can see the blue line gets further and further up, and I've set a cap on it at a maximum of 3, but it's theoretical to go as far as you want. All right, so as I come back down, the two lines will meet at an a value of 1 because there's no change when it's multiplied by 1. Then when I go below 1 into fractions, you'll see that the blue line gets closer to the x-axis. All right, so to sum it up, a dilation from x pushes the y value up or down. All right, so remember that. Dilation from x pushes the y value up or down. All right, I'm just going to delete this writing to the right-hand side here, and we will move on to dilation from the x. So looking back at the Desmos graph, I'm going to turn off dilation from the y. Looking back at the Desmos graph, we'll turn off the dilation from the x, and we'll turn on dilation from the y. Now, just as promised, dilation from the y is a horizontal change, and you can see here that when I move these points, the y values have stayed the same, but the x values have changed, and that makes it a little bit more tricky to calculate and use our notation for. So just looking at this one here, the initial point was 36.6, so the square root of 36 is 6, but the new point has been moved towards the y value, towards the y-axis, and it's been halved, so it's now 18.6. All right, so hopefully you notice that the relationship here, a equals 2, but when it's been pushed towards the y-axis, we have to use the opposite of a equals 2, which is a half. All right, so dilation from the y-axis, being tricky, and because mathematicians don't like to make things easy, dilation from the y-axis has to be read as 1 on a. All right, so if a equals 2, the dilation is 1/2. And to use this example on the screen in front of you, and I'll use the notation that we started looking at yesterday. All right, so your first port of call is your point. So you've got 36.6, and this equals xy. Now you've got your new point, which is 18.6 equals the image. So let's have a look. We know that the y stayed the same, so the original y equals the image of y. However, the x has changed. So if I say the image of x is equal to 1/2 of x, we can see that. So 18 is 1/2 of 36. All right, then I have to rearrange this to get x equals. So it's going to become x equals 2 times the image. So whatever the image is, multiply it by 2, and that was the original point, which we can go 18 times 2 is 36. Then I'm going to substitute this and this in place of the original function. So the original function was y equals root x, and then I'm going to go y image, because y's were the same, and instead of x, I'm going to go 2x image. So you can see there that this number in here is a dilation factor. It is a, but we have to read the effect as 1 on whatever that number is. So we notice that it's a 2, which means the dilation factor is 1/2. All right, so this jumps out here, and we could say that the dilation factor is 1/2. Dilation from the y-axis is 1/2. All right, so just come back to the Desmos screen. We'll have a look at a few other points to make sure that that's what's happening. We'll move the a value to, I don't know, 3. You might notice here that as I moved that line up, it got closer to the y-axis, and that was because when you read this effect, you have to read it as the opposite of that number. So if you recall the x dilation from the x-axis, when it was a fraction, so if a equaled a third, and that moved the dilation from the x-axis, that moved it towards the x-axis. All right. When it's the y-axis, if dilation is 3, we read that as a third, which in turn is moving it towards the y-axis or to the left. All right. So to recap this entire thing, dilation from the x-axis is a vertical change and can be read straight off. It occurs outside the function. So whatever is happening to x happens, and then you multiply it by the dilation factor. Dilation from the y-axis happens inside the function before anything else happens. So this is from the y-axis, sorry, from the x-axis, and this is from y. All right, the y-axis you have to read as 1 on a. You cannot read as the original a value. All right, now the last thing in this set before we look at some problems and examples are reflections, and we should be fairly familiar with these. There are two ways we can reflect. We can reflect a function, square root function again. We can reflect a function across the y-axis. When I say reflect, I mean imagine that this is a mirror and you are standing on one side and looking into it. So if you're standing here and looking into it, it would look like you could see a function stretching away from you, and that's the reflection. So if that mirror is on the y-axis, that's reflected across the y-axis. The other reflection is across the x-axis, in which case the function would be down here. All right, so two types of reflections. We can go across y or across x, and we'll have a look at the first of all, across the y. So imagine this point here, which is given by xy, has been pushed across here to this location, and you can pretty clearly see that location is minus x, the same y value. So when you reflect across the y-axis, the x values change, and the same thing will happen to this point down here, but the opposite. So this point here has been reflected down. You can see the x value is going to stay the same, so it's going to be x, but the y value is going to be the opposite. So to look at that in terms of notation, this is going to be, sorry, I'll put it in the right spot. Across the y-axis, you'll see that x, y maps to negative x, y. And across the x-axis, you'll see that xy maps to x, comma, negative y. All right. So for across the x-axis, we can then go on to say that the image of x equals the opposite of x, and y equals its own image. And for across the x-axis, we can go on to say that x equals its own image, and that the image of y equals the opposite of the original. All right, so those two things are fairly straightforward. I won't go any further into those until we come to do an example with them, but it might be also handy to note that across the y-axis, we can also write it like this using function notation, and across the x-axis would be written like this, because f of x is the same as saying y. So these are probably handy things to note down and remember. You definitely want to have this in your book with a description of what it means. So all of this, and maybe a drawing or two as well to show what you're talking about.